Hello, I'm the chemistry guy. In this video, we will learn more about atomic structure and in particular learn about the atomic orbitals and how those orbitals correspond to the periodic table.
The presentation called Atomic Structure, we learned that electrons are particles that also behave as waves. This is known as the particle-wave duality, and in fact, all objects that are moving have this particle-wave duality, but the electron is the only particle that is small enough that this is actually a measurable amount. The wave function describing the probability density of an electron can be solved for the hydrogen atom, and these wave functions in essence depend upon three quantum numbers, n, l, and m. As we learned earlier, the quantum numbers also have the following rules. N is an integer 1, 2, 3, etc. For each value of n, L can be 0 up to the number 1 less than n, and for each value of L, M can be from minus L up to positive L. Again, to review, n is called the principal quantum number, and it determines the size of the electron density contour, which is just called an orbital. Okay, as n gets larger, the orbital gets larger, and on average, the electron is further away from the nucleus. L determines the shape of the orbital, and each value of L has a one-letter designation. If L is 0, it's an s-orbital or spherically shaped. If L is equal to 1, it's a p-orbital. L is equal to 2, it's a d-orbital, and L is equal to 3, it's an f-orbital. M determines the orientation of this orbital or electron density contour, and in general there are 2L plus 1 such orbitals for each value of L. We also learned that electrons have a magnetic moment, that kind of like a little magnet, and we call this the electron spin. It is denoted by the quantum number s. S can have values of -0.5 and 0.5, which we call spin up and spin down. Therefore, the electron in an atom is labeled by 4 quantum numbers, n, l, m, and s. Finally, the Pauli Exclusion Principle states that no two electrons in an atom, or even in a molecule, can have the same 4 quantum numbers. This means that a specific orbital, which for an atom is a set of allowed values of n, l, and m, it can hold only at most 2 electrons, one spin up and one spin down. If an atom only has a single electron, the energy of the electron is only determined by the value of n. This means that the 2s and 3 2p orbitals all have the same energy. As soon as a second electron is added, this is no longer true. Here we will use the periodic table to see how the orbital energies are affected as more electrons are present in the atom. The simplest atom is hydrogen, which generally has only a single proton in the nucleus and a single electron around it. It therefore has an elemental number of 1 and is up here in the upper left-hand corner of the periodic table. This electron will go into the 1s orbital, so we denote the electronic configuration as 1s1, where the superscript 1 is the number of electrons in this orbital. Helium has 2 protons in the nucleus and therefore has 2 electrons around it. The second electron also goes into the 1s orbital. One of the electrons will have a spin up and the other electron will have a spin down, and the electronic configuration is 1s squared. These 2 electrons are all that will fit in the n equals 1 orbital, which is called the first shell. The column at the right are all closed shell atoms right here and are called the noble gases. Lithium has 3 protons in the nucleus and 3 electrons around it in the neutral atom. The first 2 electrons again go into the 1s orbital, one spin up and one spin down, and the third electron goes into the 2s orbital. Therefore, the electronic configuration is 1s squared 2s to the first. Beryllium has 4 protons in the nucleus and 4 electrons. 2 electrons go into the 1s orbital, and the other 2 go into the 2s orbital. Again, the 2 electrons in a given orbital must have opposite spins, one up and one down. The electronic configuration for beryllium is 1s squared 2s squared. Now remember, it is not a filled shell because you've still got all of the 2p orbitals in that second shell, so that's why it's sitting next to lithium. Boron has an atomic number of 5, therefore it has 5 protons in the nucleus and 5 electrons around the neutral atom. 2 electrons go into the 1s orbital, 2 go into the 2s orbital, and the 5th electron goes into a 2p orbital. Remember, the 2 electrons in the 1s and the 2 in the 2s have to have opposite spin. The electronic configuration of boron, therefore, is 1s squared, 2s squared, 2p to the first. Carbon, atomic number 6, has 6 protons in the nucleus and 6 electrons around it. Its electronic configuration is 1s squared, 2s squared, 2p squared, or 2p to the second. Since the electrons are negatively charged, they repel each other. Therefore, the 2 electrons in the 2p orbitals will be in different orbitals, okay, different values of m. There is a slight advantage of having the same spins. The magnets will be aligned, so they will both be spin up, for example, when aligned with an external magnetic field. The electronic configuration for nitrogen, which is atomic number 7, is 1s squared, 2s squared, 2p to the third, where each of the 3 electrons in the 2p orbitals will be in different orbitals and will all have the same spin, all spin up or all spin down. Oxygen, atomic number 8, has 8 electrons around the nucleus, so its electronic configuration is 1s to the second, 2s to the second, 2p to the fourth. 2 of the electrons in the p orbitals will have to go into the same orbital, so one must be spin up and one must be spin down, and the other 2 will go into separate p orbitals with the same spin. Fluorine has 9 electrons, is atomic number 9, okay, and its electronic configuration is 1s squared, 2s squared, 2p to the 5th. 2 of those 2p orbitals will be doubly occupied, one spin up and one spin down, and the third 2p orbital will only contain a single electron. Neon completes the second row of the periodic table. It is atomic number 10, so it has 10 protons in the nucleus and 10 electrons around it, and it will fill all of the 1s, 2s, and 2p orbitals. Its electronic configuration, therefore, is 1s to the second, 2s to the second, 2p to the sixth. It is a closed shell system, and it is the second member of the noble gases. Jumping around a little bit, we can see that we have a noble gas whenever a set of p orbitals within a shell, which is a value of n, is filled. Argon is the third noble gas and has an electronic configuration of 1s squared filling the first shell, 2s squared 2p to the sixth filling the second shell, 3s squared 3p to the sixth filling the third shell. It is considered a closed shell system even though there are 3 d-orbitals present that are unoccupied. So again, noble gases only really are filling the s and p orbitals of a given shell. Looking at the 4th row of the periodic table, the first 2 electrons go into the 4s orbital, the next 10 electrons go into the 3d orbitals, and the final 6 electrons go into the 4 p orbitals. The electronic configuration for krypton is 1s squared filling the first shell, 2s squared 2p to the 6th filling the second shell, 3s squared 3p to the 6th, 4s squared 3d to the 10th, 4p to the 6th. This is cumbersome, so instead we can just write argon AR 4s squared 3d to the 10th, 4p to the 6th, where AR just means the electronic configuration of argon, which takes care of the first and second shells, the 3s squared and the 3p to the 6th. Things get a little crazy when we get to the 6th row of the periodic table, because as you can see here we have a breakout, which is the lanthanide series, which actually represents the 4 f-orbitals. So as we start to fill across, the first 2 electrons will go into the 6 s-orbitals, okay, and then we put 1 into a 5d and jump down here. So by the time we get to lutetium, which is atomic number 71, the electronic configuration is 6s squared 4f to the 14th 5d1. From there, we fill up the rest of the 5d orbitals, so that by mercury, which is here atomic number 80, the electronic configuration is xenon, to fill up to there, and then 6s squared 4f to the 14th 5d to the 10th. Then we add the next 6 electrons to the 6p orbitals to get radon, atomic number 86, and therefore its electronic configuration is xenon 6s squared 4f to the 14th 5d to the 10th 6p to the 6th. As you've probably figured out, the periodic table has the following form. Each row corresponds to the quantum number n. So as you go across for the s and p orbitals, they get larger for each of the atoms down the row for the outermost electrons. The first 2 columns are for the s-orbitals. These columns over here are generally for the p orbitals. In the middle, we've got the d-orbitals, but the d-orbitals are for the quantum number 1 below the row. So even though this is the 4th row, these are the 3 d-orbitals here. And then we've got the lanthanides and actinides down here that correspond to the f-orbitals. Okay? And they are for the shell 2 lower. So again, when I've got the 6s, I then go to the 4f's, the 5d's, and then the 6p's. The only exception to this periodic table is helium. Some periodic tables place it above beryllium, since its electronic configuration is 1s squared, or 2 electrons in an s orbital. But since it fills the n equals 1 shell, most periodic tables place it in the last column so that all of the noble gases are together. The noble gases are very stable, and other atoms, if possible, would like to look like a noble gas. Therefore, lithium, which is basically the 2 electrons in the 1s plus a single electron in the 2s, easily loses an electron to become lithium plus. Remember, that's called a cation, or just an ion, so that its electronic configuration is the same as helium. Calcium will lose 2 electrons, forming Ca2+, so that its electronic configuration is the same as neon. Losing an electron is easier as the atom gets bigger. In other words, as the n, or the shell of the last electron, gets larger. At the other extreme, fluorine and chlorine would like to gain an electron to become F- and Cl-, the anions, so that they look like neon and argon respectively. Okay, this will fill either the second shell or fill out the 3s and 3p electron orbitals. The desire to gain or lose an electron is called the electronegativity. Atoms with a low net electronegativity will lose electrons, and those with a high electronegativity will want to gain electrons. Therefore, the electronegativity increases from the lower left of the periodic table to the upper right, not counting the noble gases, since they already have the desired electronic configuration. So again, the elements down here in this corner have the lowest electronegativity and will easily lose an electron or two electrons depending upon what column they're in, and it goes all the way up to here with fluorine and chlorine having very high electronegativities because they want to gain an electron so that they look like the noble gases. Carbon is in a weird position. Its electronic configuration is 1s squared, 2s squared, 2p squared. Therefore, it would have to lose 4 electrons from the n equals 2 shell or gain 4 electrons in order to look like a noble gas. Neither of these are possible, so instead it shares its 4 outermost electrons, called valence electrons, with an electron from up to 4 other atoms, so that it effectively has 8 electrons in this outermost shell. This is known as the octet rule. Okay, we will talk about chemical bonding in atomic orbitals, molecular orbitals, and bonding. As a final point on the periodic table, the elements are put together into various groups. In the first column, with the exception of hydrogen, we've got the alkali metals, and they will all want to lose an electron. Okay, in the second column are the alkaline earth elements, and they want to lose 2 electrons. Through here, we've got the transition metals. We then have the metals. We know that aluminum is a metal. These are called the metalloids. Okay, silicon is a semiconductor used in computer chips because it kind of allows electrons to flow. Then hydrogen and this group right here, which is the great majority of the chemistry in our bodies, are nonmetals. They only want to form bonds generally, though hydrogen can lose an electron. The next group are the halogens. They want to gain an electron so that they look electronically like the noble gases. Then down here we've got the lanthanides and we've got the actinides. Please note that this picture is not mine. I got it from the web, and they messed up on the colors between the lanthanides and actinides. Lanthanide should be the light purple, and actinide should be this salmon color.
I hope you enjoyed this video, and if you enjoyed it, I hope you will support my Patreon page.